here we're going to be discussing all of the equilibria related to hemoglobin, and I want to start with just drawing a picture of the iron when it's in complex with oxygen. It's in the plane, so there's some likelihood that we'll find the iron and the distal histidine in this location. And that's in equilibrium with the out-of-plane position, where the magnetic properties of the iron make it so it doesn't fit in the plane of the heme. And I'm probably exaggerating some of this structural transition, but there is these two possible positions for the heme iron, and one is in plane and one is out of plane. And these are associated with binding oxygen, so an oxygen release. So we'll have here a hemoglobin bound to a certain number of oxygen molecules, and I'll just try letting go of one of these oxygens. So oxygen dissociation. And these equilibria are linked with this structural transition for the quaternary structure that we call the R relaxed form and the T form. Remember, T is the one where there are a lot of salt bridges constructed with 2,3-bisphosphoglycerate at the center, and in this TENS form, we're much less likely to be binding oxygen. We're preoccupied with this arm wrestling match with the salt bridges, but in the relaxed form, when we've broken those salt bridges, now we're free to reposition this proximal histidine, and that allows the iron to go into the plane, which favors the binding of oxygen. In addition to these, we can write the uptake of 2,3-bisphosphoglycerate. So we make that complex, and there's just one 2,3-bisphosphoglycerate per hemoglobin tetramer, and meaning you can only bind one molecule. You can't bind a fourth of the molecule, and that helps to explain why this transition between R and T states is so cooperative, that once you have made an opportunity for binding 2,3-bisphosphoglycerate, you're much more likely to lock all of the subunits, all 4 subunits, into this TENS form. Then there's the role of protons. So there's, let's say, n protons, a certain number of protons, and they are binding at conjugate base groups in the hemoglobin structure. And these are, for example, we have histidine in the neutral form potentially interacting with a carboxylic acid functional group, and once it takes up this proton, then we can construct a more stable interaction with this carboxylate group to form a salt bridge. And then there's one more to draw here, and that has to do with the uptake of carbon dioxide. So there's some primary amine that chemically reacts with the carbon dioxide to form a carbamate group, which has a negative charge. And these new negative charges in the carbamate, they're able to form additional salt bridges. So as I've drawn all of these equilibria, they are all lined up so that on the right-hand side we are favoring the T form of the structure, and on the left-hand side we're favoring the R form. And it's not entirely obvious, but each one of these equilibria is linked to all the other ones, such that if you go from left to right for one of these equilibria, you then favor in a mutual reinforcing way to go from left to right in all the other ones. And likewise, if you go from right to left for any one of these, letting go of protons or releasing 2,3-bisphosphoglycerate, that will then encourage the binding of oxygen, the iron going into the plane. And so all of these equilibria are influencing the other equilibria, and it's a linked system of simple equilibria, which then imparts relatively complicated and almost intelligent-like properties to hemoglobin.